Alright, so now we're going to look at the derivative as a function. We've been looking at derivatives as the slope formula, the limit as h approaches 0 of f of a plus h minus f of a over h. Now we're going to look at the derivative as a function and try to find an actual formula. So far we've been finding a number for the derivative at a point. Now we're going to find a formula so we can find the derivative at any point. Okay? So things that we'll know to do, we'll know the derivative of f is the function whose value is the limit as h approaches 0 of f of x plus h minus f of x over h, provided the limit exists. We'll know our function notation, okay, which we'll look at in a minute, and we'll know that the derivative can be represented graphically, numerically, analytically, and verbally. And today mostly we're doing the analytical, which would be, a formula, okay, more than anything, a formula. Good. All right, the definition of the derivative. Okay, the derivative of a function f of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, and we're going to do something very similar to what we did yesterday. But several things. First of all, let's talk about the notation for a derivative. There are several ways we can notate it. One of our common ways is this, f prime of x, or dy dx, or d dx, which is, eventually we'll use those as fractions, but for now we just use them, it says it's d dx, and y prime. Those are all common notations for a derivative. We also have second derivatives, which are most common. We call a higher order derivative. I mean, there are third and fourth derivatives, but mostly we deal with the, okay, so f prime or y double prime, okay, or you could have d squared y over dx squared. That also means a second derivative, which you'll deal with. And so now what we're going to learn is how to use this definition of a derivative to find a formula for a derivative. Okay? Before we do that, we have to remind ourselves some stuff about binomial expansion, or a binomial where you have something like x plus a to the n power. And we're going to look at that, and Pascal's triangle is going to help us with that. Okay? So, Pascal's triangle, you can see how it works, and you can recreate it quite easily. You start with a 1, and then 1, 1, and then 1, and then you do 1 plus 1 is 2, and then you end with a 1. And then you start the next row with a 1. 1 plus 2 is 3. 2 plus 1 is 3, and you end the row with a 1, and so on and so forth. And you can recreate the whole thing by doing that. You can see down here it gets all bunched together, and we won't go quite that far down. But this starts out, this is actually row 0. So when you know that, row 0, if you see right here, this is the row indicator. So that you start here in 1, this is row 1, row 2, row 3, row 4, row 5, row 6, and so on and so forth. Goes all the way down just like that. So just for example, let's say we want to do x plus a to the 5th power. So we use row 5. And row 5 would be right here. Here's row 5. And we use, those are our coefficients. So those are our coefficients. Okay. So I'm going to have 1, 5, 10, 10, 5, and 1. And now I start with the first one here. It'd be x to the 5th. And then as I go, it's going to be x to the 4th next. And then x to the 3rd. and then x squared, and then x to the first, and then x to the 0, which of course just disappears. Now you can go that way, and then you come back using the other one. So it'd be a to the 5th, and then a to the 4th, and then a to the 3rd, and then a squared, and then a to the 1st, and then of course a disappears. So the first and last terms have one variable in them. Okay? And that would be the binomial expansion. If we multiplied it all out, we did FOIL, we distributed, we did everything we had to do there, this is what we would get after a long, tedious process. So the Pascal's triangle makes binomial expansion a lot quicker, a lot easier. Okay? And in fact, if we do x plus h to the 4th, I'll show you another little trick that makes it even easier. So that would be 4th row right here. So it'd be 1, 4, 6, 4, 1. And then again we start x to the 4th plus x to the 3rd. Now, if you notice back up here, and we're going to apply it down here in a minute, but we come back up here, this said x to the 5th. And then x to the 4th, a to the 1st, 4 plus 1 is 5. And then x to the 3rd, a to the 2nd, 3 plus 2 is 5. And then x squared, a to the 3rd, 2 plus 3 is 5. So it always added up to this power that was in front here. So I have x to the 4th. Now I have x to the 3rd. I need a to the 1st power, because then 3 plus 1 plus x goes down, and as x goes down, a is going to go up. So a, and then a squared, and then 4, this would be x to the 1st, and then a goes up again to the 3rd, plus 1, a to the 4th power. That is binomial expansion. We're going to use that in our next example here. Okay, so I'm going to clear out the drawing on the Pascal's triangle here so that we can refer back to it. Alright. So, we want to use binomial expansion to find the derivative if f of x equals x cubed minus x. Find a formula for f prime. So we know we're going to use the limit as h approaches 0 of f of x plus h minus f of x all over h. So we're going to take the x plus h is going to be plugged in to there, and the f of x just is that function. This is f of x. So we're going to plug in x plus h in here. That would be x plus h cubed minus x plus h. Putting x plus h in place of the x. Minus, don't put parentheses around that. Always put parentheses around that second one. And then the function is just x cubed minus x all over h. So still the limit as h approaches 0. Now is where we have to use binomial expansion, because what should happen here when we're doing this is everything that does not have an h in it should cancel out. If it doesn't, we've done something wrong, because it should cancel out every single time. Okay, so let's go back. We need to do x plus h to the 3rd power. So we have to go back, and we go to row 3, which is right here, 1, 3, 3, 1. So you're going to do a lot of algebra here. So it's going to be the limit as h approaches 0. And we're going to do 1, 3, 3, 1. And it would be x cubed plus, and then x squared and add the h, plus x, the value, the exponent goes down for x and up for h, and then the x disappears and it's h to the 3rd. So that goes here. So it's x cubed plus 3x squared h plus 3xh squared plus h cubed minus x plus h minus x cubed minus x all over h. Now we're going to distribute this negative So I would get x cubed plus 3x squared h plus 3xh squared plus h cubed minus x minus h minus, and just leave this the way it is here, all over h. So once we've got that first one set, once this part here, before, not including the end function, the second part, if that's all distributed and everything is, and there's no parentheses anymore, now we're ready to cancel. Because everything in this one, this second one, everything in here should cancel. So I have x cubed. Sure enough, x cubed minus x cubed, they cancel. I have negative x. I have negative x minus negative x. Those cancel. So everything without an h in it canceled as it should. So now I have 3x squared h plus 3xh squared plus h cubed minus h divided by h. Okay. So each of these terms has an h in it. So I cancel. So this h is going to cancel out with this one, and it's going to make this 1. And then it's going to cancel this out and make it h squared, and it's going to cancel this out and make it just h. So I would have 3x squared plus 3xh plus h squared plus h squared minus 1. And now the h is gone, so now I can plug in 0 for h, which would mean this one would be left, that one would disappear. If I plug in 0 for h, that's going to just go. If I plug in 0 for h, that's going to go. So I have there. So f prime of x would be 3x squared minus 1. Now we can use that to find the slope, find a rate of change. Anything that we need to do, we can do right here now that we have a formula for our derivative. Alright. So let's do the next one. Same idea. We still have to do the limit as h approaches 0 of f of x plus h minus f of x over h. And again, I have to take this x plus h and plug it in for x in this function. And that's going to give me 3 and then x plus h to the fourth minus 2 times x plus h squared minus, and then we put the function f of x right there, so 3x to the fourth minus 2x squared all over h. So again, I have to expand this whole thing, and I have to do it twice. I have to do it with x for x plus h to the fourth and x plus h squared. So I'm going to go back to Pascal's triangle again. Okay. And this time we're not interested in row 3 anymore. We're now interested in row 2 and in row 4. So row 4 is 1, 4, 6, 4, 1, and row 2 is 1, 2, 1. So let's go back down here and go over, and we have our 2, 1, 4, 6, 4, 1, and 1, 2, 1. Now I'm going to expand. It's going to be 3 times that, and it's going to be 2 times that. I don't want to forget that. So it would be x to the fourth plus 4, and then x to the third, drop the exponent, now we bring the h in, plus 6x squared, move the exponent down 1, and for the h we move the exponent up 1, plus x h to the third plus h to the fourth. Alright, now we do the second one. So x squared, so it'd be x squared plus 2x, and then we bring the h in, plus, and then h squared. So this would be 3x to the fourth plus 12x cubed h plus 18x squared h squared plus 12x h cubed plus 3h to the fourth. That would be distributing that 3 to all of those. Here if we distribute the 2, it would be 2x squared plus 4xh plus 2h squared. We're going to put those in here now in place of this and in place of that. So we got a minus sign too, so we need to put this all in parentheses after that minus sign. Then it would look like this: 3x to the fourth, we still have the limit as h approaches 0, plus 12x cubed h plus 18x squared h squared plus 12x h cubed plus 3h to the fourth, all over h, but minus, and then 2x squared plus 4xh plus 2h squared, and then minus 3x to the fourth minus 2x squared. Phew! A lot of stuff there. A lot of stuff there. Okay? So I'm going to do this, and I'm going to change and get rid of these parentheses by distributing this negative. So I'm going to make this negative, this is going to be negative, this is going to be negative, and I'm going to change that to a positive. So now that I've done that, I don't have to rewrite the whole thing. Now essentially those parentheses are gone, so I can look to cancel this. I have a 3x to the fourth here. Do I have a 3x to the fourth over here? Yes. I have a negative 2x squared. Do I have a negative 2x squared? Yes. So those canceled. Everything left should have an h in it, and it does. So it'll be 12x cubed h plus 18x squared h squared plus 12x h cubed plus 3h to the fourth, okay, minus this 4xh, and then minus 2h, and that should be 2h squared, I'm sorry, 2h squared, okay, all over h. Since all of them have an h, I can cancel. This is going to cancel with this h and this one, and it's going to make this one h. It's going to make this one h to the third. This one's going to be h squared. This one's going to be h. Okay, and then I'll be able to plug in, so I have 12x cubed plus 18x squared h plus 12x h squared plus 3h to the third minus 4x minus 2h. And we still have the limit as h approaches 0. Now we're to a point where we're no longer going to make the bottom of the fraction 0 by plugging in 0. So now we can plug in 0 for h. So essentially any of these terms that has an h, still has an h in it, is going to drop out because we're putting a 0 in here. So this one's going to be gone because that would just be 0. This would just be 0. This would just be 0, and that would just be 0. So it would be 12x cubed minus 4x. That would be our derivative of this function, 12x cubed minus 4x.